All right, so here's the last chapter 8 topic. I sort of shuffled the chapter. I want to talk about bond energies and bond lengths before I talk about resonance. You'll see why in a little bit. Definitely want to talk about Lewis structures before this as well. And so I move it all the way to the end. I don't believe the book did. I think I shuffled it around. So just if you're reading along, be aware that that happens. So resonance is actually a really important idea in chemistry. It's a reality, not just an idea. A lot of times when you're like, oh, something's behaving weird, a molecule's doing something unexpected, defying, those early, like I said, I like to build those chemical instincts. So sometimes there's electronegativity stuff that interferes. The other thing is resonance structures. Most of the time when I was in graduate school and somebody would be giving a presentation on something that was unexpected or weird, a resonance structure was the underlying cause of that. Like, it felt like it was like 9 times out of 10. I don't know. Look, it's farther and farther in the rearview mirror every year, but that seemed to be the case. Like, this is a really important idea in chemistry, has dramatic effects. This is why vinegar is acidic, all kinds of things like that. Like, it is definitely in play. So, the kind of, legal definition of resonance. So if you've got a molecule and you have 2 or maybe more Lewis structures that are all equally valid, like, nothing like formal charge or anything like that can throw them out. So you didn't just draw something totally crazy, but there are 2 that, you could be, the left option or the right option, or maybe there's a third option. And there's no way that you can decide which one is exactly the best because they all tie. Well, then you have a resonance structure. And so what happens is it's a blend of all 3. It's not option A, B, or C. It is constantly moving between the 3. And we'll explain that more in a little bit. And so what you get is this weird kind of hybridized structure. It is all 3 of them blended together. So it sort of splits the difference. So it is a blend of all of our equally correct Lewis structures. And so a really good example of this is nitrate. And so there's a couple ways we could draw this. So I'm going to draw all the nitrogens in black. Move this one over just a little bit more room here. So we got option 1, 2, and 3. Okay. And we're going to have lone pairs on there. So nitrogen can't break the octet rule, so there's nothing like that happening here. And I'm going to use the same color. So this is the same oxygen on the left of all of these. We're going to have the same oxygen on the right. So I'm not moving atoms around. Let me be clear about that. And then on the bottom, we'll have the green one. So I want to be clear. Like, I'm not rotating the molecule. I'm not doing anything like that. I'm not making any of that happen. And then we're going to bracket it in. So I haven't drawn the bonds yet. But I just want to be clear. We're going to have 3 nitrates. The right oxygen is the right oxygen. It's the same one on all 3. There are 3 different structures we can draw here. So what I can have, oops, I don't actually have a lone pair there. That was my mistake. I can have a double bond going to the blue oxygen. I could have it going to the green, or I can have it going to the purple. All of those are valid options. If I were to work up formal charges on these, I would see that what I have, I'll use red because it's the only color I got left, but I get a 0 here, a -1. Oops, I forgot my lone pairs. All right, so we'll have 3 lone pairs around the oxygens with a single bond, and then the one with the double bond gets 2. That's what we have. Okay, sorry about that. All right, so these are -1s. That's a 0, 0. Oops, that's a -1. 0, -1. And then the nitrogens are all +1. You can do the formal charge calculations on this, verify that I'm correct. But ultimately it adds up, -2 + 1 -1 overall total. So we are going to have non-zero formal charges because we are dealing with something that has a total charge. So that should be expected from our earlier discussions. So how do you decide? Is it option A? We'll note these, A, B, or C? Well, these are all equally valid. Formal charge isn't helping us decide. The octet rule is being followed across the board. Nitrogen has to, so we can't break the octet rule. So what do? We go, oh, this has a resonance structure. It can be double bonded to any of these oxygens. It doesn't matter if it's blue, green, or purple. One of them's going to get a double bond, two of them are going to get single bonds with 3 lone pairs. That's what's going to happen. And so what happens is, in reality, we get a mix. We get a mix of A, B, and C, i.e. a resonance structure. Okay. And so how do we draw a resonance structure? You guys are going to love this. All right. So it's still an ion. We're not going to worry about the lone pairs. We got our 3 oxygens. I'm not going to worry about coloring them anymore. Get a minus charge. Okay, so they all definitely have, I got a little excited with these single bonds. They're a bit, large. All right. They all have a single bond, but where's the double bond going to be, right? Well, the answer is it moves around. So we put a dash in here. That's our resonance structure. Right there. What we have is, this is not a single bond. I wonder if my microphone's picking up how squeaky this marker is, by the way. Or a double bond. It's about a 1 1/3 bond, because this double bond is getting shared in 3 locations. So they all have a whole single to themselves, and then this one has a third of the double bond, this one has a third, and this one has a third. Now in reality, that double bond isn't 1/3 in all locations. What's happening is it is switching very fast around all over the place. So sometimes, if we took an instantaneous snapshot, we might see this, this, or this. But if we watch it, what we actually see is this. Because the electrons are small, they can move very, very, very fast. So they're like, the running back or the wide receiver on a football team. They are very fast and they are not very big. Well, some wide receivers are getting a little large, but not compared to like a lineman. They can move very quickly. These nuclei are much, much larger, like 2,000 times larger at least than the electrons. And so they are slower to respond. And so they're like, oh, I have a double bond. I need to sneak in closer to my central atom. Oh, I'm a single bond. I need to get away. Back and forth. Well, the electron makes a double bond that makes a single bond. And so what happens? I'm stuck in the middle. I'm trying to move away. I'm trying to move back. Guess what I have? I have a bond distance that is less than a single bond, but more than a double bond. My bond energy is going to be about the same. It's going to be more energy than a single bond, less than a double bond. And it's going to work out to be about somewhere around 1 1/3, because 1/3 of the time I'm in the double bond situation, 2/3 of the time I'm in the single bond situation. So I'm just sort of stuck in between. This isn't a quantum situation. I can move in the middle there somewhere. I'm not a double or a single. I can get caught. And that's what happens. So this is a really tricky idea. And so I'm sure there'll be questions. Please use the forum. I'm feeling like one of those big football players right now, let me tell you. So there's this unwritten rule of football, I think, where if you are over 300 pounds and you score a touchdown, you get to celebrate till you need, you get to get Darth Vadered with the oxygen mask, turn on the valve, pure O2. I'm feeling like that right now, but hey, we did it. We got through all of chapter 8. Resonance is a crazy idea, but just recognize that it's only if you can just move electrons. So I've essentially just shifted my double bond down here, and I've put a lone pair here. I've only moved electrons. I haven't moved any of the nuclei. That's what makes these identical. So if you're redrawing, if it's just a rotation or you're flipping or something like that, that is not a resonance structure. You cannot move any atoms. You can only move electrons, and that's what I've done here. So again, if there's questions, forum's the place to go. I suspect that this will be one where there's a lot, because this is a tricky topic. Like I said, this leads to a lot of the cutting edge modern, there's something weird happening in chemistry, let's talk about it level research. So resonance is incredibly important, very intricate, very complicated, really big idea if you're going to take organic chemistry. This drives a lot of reaction pathways and things like that. So it is an important idea, but it is not necessarily a simple one. And so for this class, it's really just tying it into these Lewis structures and what that means for bond lengths, bond energies, and drawing resonance structures. Notice I left out the dots. We don't really worry about the lone pairs because they're all switching all over the place. It all just goes to hell, whatever. We don't worry about it. All right, so there we go. I'll have one whole chapter on Moodle this week. Class doesn't even start for like a week and a half, so we're off to a good start so far. Hopefully I won't need to wheel any oxygen tanks in here for the longer chapters, but we'll see. And yeah, thanks for hanging in there.